Okay. Okay. I think we are live. Welcome, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host. Today, we're presenting Event Horizon Telescope Imaging and Models of Sagittarius A star in the Galactic Center by George Wong. George got a bachelor in physics, mathematics, several bachelors actually in physics, mathematics, and computer science from New York University, and then his PhD and master's from the University of Illinois at Urbana-Champaign, where he worked with Professor Charles Gammie. George is currently a member of the School of Natural Sciences at the Institute for Advanced Study, an associate research scholar at the Princeton Gravity Initiative at the Department of Physics in Princeton. George is also a member of the Event Horizon Telescope Collaboration and the Horizon Collaboration. So he's going to talk about some of the recent results there. George's main research is devoted to studies of models or accretion onto supermassive black holes and the connection between black holes and relativistic jets. And he's an expert on all these models, and we're going to hear a little bit about that today. So we are delighted to have him in our webinar series today, which is the last of this season. So stay tuned for the next ones. And remember that you can ask questions over email through our YouTube channel or YouTube or even Twitter. And then the questions will be read at the end of George's talk. So without further ado, we will turn the time over to George. Thanks for joining us.
Thank you, everyone. Thank you for having me. I'm going to try and share my screen now. And hopefully everyone can see this.
Perfect, yes.
Great. So, as Alejandro said, I am a member of the Event Horizon Telescope Collaboration. And today I'll talk a little bit about the imaging efforts and modeling efforts that went into analysis of the data that the Event Horizon Telescope Collaboration took in 2017. And again, I just want to thank the organizers, coordinators for giving me the opportunity to talk about this. I think it's really exciting. Okay. So here's a short little outline of my talk. You can think of it as being in maybe 2.5 sections. So first, I'll kind of go over what the Event Horizon Telescope actually is physically and kind of how it works. And we'll get into some detail later on about this. But the main thing that I want you to take away from this first section that I hope I'll be able to motivate is that there are parts of the data, there are parts of the image that you can trust, and there are some parts that you should trust less, perhaps. And so it's important to understand what goes into making the image so that we can understand what parts of the image to trust. So that's the first part of the talk. Then in the second part, I will talk about the astrophysical modeling that went into actually interpreting the data after we had taken it and kind of understood the uncertainties. So I'll talk about the physics of accretion and then the precise constraints that we applied and kind of what they meant. And then after that, I'll talk about the future, especially in the context of these astrophysical models. One thing that I feel it's important to point out is that the Sag A star, the Galactic Center set of papers that we published were in total, depending on what exactly you count, about 400 pages. There's no way that I can cover 400 pages worth of content here. So again, I'm just going to be talking about the imaging efforts and the theory, but that does not mean that this is all that we did. We had other tests of, for example, general relativity that I will not be discussing now. Okay. So what is the Event Horizon Telescope? I think it's best to start with a bit of motivation for what the Event Horizon Telescope aims to do. So what is the goal of the Event Horizon Telescope? And in a sentence, it's to produce images, whatever that means. It's to produce images that are really, really high resolution so that we can actually see the event horizons around nearby supermassive black holes. And so I have this animation that was produced by the European Space Agency that is showing kind of the scales involved with this question. So the nearest supermassive black hole is at the center of our galaxy. It's supermassive, it's very large, it's millions of times the mass of the sun. But at the end of the day, it's also quite far away from us. So it's very small. And so what you just saw in that movie was kind of scanning through, if we were to look up into the sky, if you were to look up into the sky at where the galactic center should be, what would you see? I'll play that movie again. What would you see in optical? And so here you can actually, see the dust in the way. If you change over, instead of optical, if you change over to radio, you can kind of see through some of this dust. And there are all of these really interesting structures on larger scales that I will not be talking about at all. But again, this movie, this animation is just to kind of give you a sense of scale of how far in you have to zoom to see things. One of the typical size comparisons that may be a little bit more grounded, maybe more comprehensible, is that if you were to place something like a quarter or a coin on the moon, on the surface of the moon, and look at it, you want to try and resolve features of that size. This is a rather challenging task. So how do you do this? Well, you may remember that it's pretty hard to get high resolution if you don't have a very large instrument. So there's a natural kind of earthbound limit for how large you might be able to make your telescope. And that limit in size is, of course, the diameter of the Earth. So in principle, the largest telescope you could make on Earth would be a telescope the size of the Earth. Of course, there are issues. You can't actually make a telescope the size of the Earth. But what you can do is you can take a whole bunch of different telescopes that are all over the planet and link them together through this VLBI, very long baseline interferometry method that I'll talk about on the next slide. But I thought it was a good idea to show this other animation that was, again, made by the EHT, kind of showing where all these telescopes are. That's what you see on this globe that's turning on the left side of the screen. And also kind of show you what all these telescopes look like. So again, these are radio telescopes. So they don't have these glass lenses. You're not going to actually look through the telescope. But they're kind of like giant antenna. And you point them up at the sky and you listen to radio frequencies. So in particular, we are listening to radio frequencies at 230 gigahertz or just below that, which if you prefer wavelengths is 1.3 millimeter. And the way that interferometers work, the way that VLBI works in general, is you take all of these different pairs of telescopes. So, in that animation of the globe or in the image of the globe, you see here there are 5 telescopes on screen, or 5 sets of telescopes, observatories on screen. And you take each pair of those observatories and you measure the distance between the 2 observatories, and you also kind of measure the orientation. So for example, there's this horizontal line between SMA and LMT. So you measure that orientation as being horizontal or maybe as being diagonal, and you measure the distance between them. And then over time, you correlate the radio signal that you're recording. You correlate the signal between those 2 observatories. And that correlated signal ends up mapping to a Fourier coefficient in the Fourier domain, and the position for that coefficient, the position for that data point, corresponds to exactly that orientation between the 2 telescopes and the distance. And so to make that a little bit more clear, hopefully, what I'm showing you on the right here is just the location of all of those different telescope separations. And so they're colored by different pairs of telescopes. But again, if you have 2 telescopes that are kind of right north-south on top of each other and they're at some distance, then it'll show up as a point kind of on the north-south or on the y-axis of these 2 plots on the right. And one thing that you'll notice is that a single color, in fact, corresponds to many different points in these plots. And that just corresponds to the fact that's just because of the fact that over time the Earth turns. And so the apparent distance and apparent orientation of every single pair of telescopes changes. This kind of changing, this evolution will turn out to be very important later on, and also kind of annoying as well. So useful and annoying, as most things are. So, right, the projected distance between each pair of telescopes corresponds to what we call a baseline. And you will notice in these 2 plots on the right, which are just 2 different days of looking at the galactic center, you'll notice that the points do not, in fact, cover the entire domain. And so we call this a sparse sample. And so one of the problems, the technical challenges associated with interpreting the data that we take is how to take this sparse sampling of the Fourier domain, how to take this sparse data and back it into kind of some information about the full image. So you may recall in general Fourier theory, if you want to learn information about everything that's going on in an image, you take the Fourier transform of the image, you still need to, in principle, know information about everything in the Fourier domain. We obviously don't have that, so we have to build some assumptions into, for example, the smoothness of data, or what do we expect in general about the overall structure, the size. So is it possible that the image is very, very large? Or what? So we have to make all of these choices. There's a lot of history that goes into kind of the best ways to solve this inversion problem. But at the end of the day, there is an algorithm that is involved in actually translating all of the data that we take into an image or into a sequence of images or a movie. And so before I talk about the actual images that we produced, I want to go back to this point about how over the period of the observation, which is maybe 8 hours to 12 hours, half a day, approximately a third to a half of the day, the points change. So some technical information is that each data point or a scan is about 10 minutes. And this is just associated with the technical construction of the actual telescopes. So it takes some amount of time to record data and so on, accumulate enough signal to noise. And so this time is approximately 10 minutes. You can lower it, you can increase it depending on technical points. But 10 minutes is a good number to have in your head. So that's one time scale, 10 minutes for a single data point, and then the course of an observation is approximately 8 hours, 9 hours. So that's significantly longer. And this raises an interesting problem in modeling the galactic center in particular. So again, I'm going to be talking about the imaging of the black hole at the center of the galaxy, which we know from various other measurements, or we have strong evidence from other measurements. This object has a mass of approximately 4 million times the mass of our sun. So if you remember the speed of light and you remember Newton's constant, you can come up with a characteristic time associated with how long should it take light to cross an object that's this massive, approximately, and that turns out to be on the order of 20 seconds. And so if you then ask the question, well, suppose I have an object that's approximately this size, and I have maybe some gas that's swirling around it, you can ask, okay, what is the length of time it would take if this gas is following, a reasonable circular orbit around the object? How long does it take for a blob of gas to go all the way around an object? And there are some assumptions about the source that go into answering this question, but it turns out that the answer is somewhere on the order of 5 minutes to 20 minutes. And this is why it's such a problem that each data point is 10 minutes long, because that means for a single data point, you're not getting a snapshot of the evolution. You're getting kind of a smeared out time average of the evolution of the source over an entire orbital time. So you have to keep that in mind. So this is point one. Point two is that, again, every single data point, which corresponds to this kind of smeared out average, every single data point is taken maybe many dynamical times apart. So you take one data point at hour 0 of your observation, and then you wait dozens of dynamical times later, and then you take another data point. And again, these data points correspond to different angles in the Fourier domain, because the Earth is sweeping, is rotating. And so you're getting information about the spatial structure in your image, which is kind of like the smeared out average image in the first place, but you're getting information about the spatial structure in one orientation, in one direction, maybe hours, dozens of dynamical times before you're getting information about the spatial structure along another orientation. And so you have to be really, really careful when you then take these two data points, these two different orientations, and kind of back them out into an image. What should you trust from the image at the end of the day? If you want to understand this from a more visual perspective, I think that the kind of plots on the right or I guess all of the plots on the slide are rather useful. So you can think of this process as happening in either, or you can try and ask the question, what are the visual correspondences of this process, either as it happens purely in the image plane or purely in the Fourier domain. And so what I'm showing you here on the top left in this graphic produced by Andrew Schell and Avery Broderick, what I'm showing on the top left is a potential image. It's a simulated image. Maybe we should see this for the black hole accretion flow. What if we saw this? It doesn't mean this is what we expect to see. It's just what if we saw this? And so that's the top left. And then kind of going from the top row to the bottom row, what I'm doing is just taking a Fourier transform. So the Fourier transform of the top image is the bottom image. It's this kind of blobby thing. The exact details of that don't matter. But what does matter is the fact that, again, when we're actually sampling the Fourier domain, right, we have a VLBI instrument, so we're not taking an image, we're taking these Fourier amplitudes. When we sample the Fourier domain, we're not seeing that full image. What we're instead seeing is that image multiplied by a whole bunch of delta functions. So in the bottom center, again, I'm just showing you the locations of where we're taking the data. And so the actual the actual data taking process corresponds to taking the truth image, the Fourier data in the bottom left, and only sampling it at all of those data points. And then at the end of the day, what you get is you get a list of numbers because you're not getting this two-dimensional data anymore. And so you can plot that list of numbers however you want. In the bottom right, what I'm showing here is just the kind of sampling the amplitudes of the complex coefficients plotted against the displacement in the Fourier plane from the zero. And that doesn't matter so much. But what I think is really interesting and what can build intuition here is that if you take the Fourier transform or the inverse Fourier transform of your coverage, of your sparse coverage, you get this kind of blocky or blobby organized or patterned structure that you're seeing in the top center. And so you have all these different blobs, these different splotches, and this corresponds roughly to the spread of all of the different data points in the Fourier domain. And I want to be very clear here. So this top center image is purely a product of the bottom center image. So it's purely a product, the dirty beam is purely a product of where your telescopes are. It doesn't matter what your source image is. This is kind of how well you can see your source image in some sense. So of course, you'll remember that multiplying in the Fourier domain is the same as a convolution in the image domain. So in principle, the best that you can do if you don't know anything else about the image is you could recover an image that looks like the top right? So you multiply your Fourier domain sampling by your UV coverage. It's the same thing as convolving your truth image with the dirty beam, and you get this kind of blobby structure. Okay, so why did I take all this time to explain what's going on here? Well, I want to, again, just emphasize that there's this natural blobby patterny structure that comes out of the dirty beam, which is just purely a product of, or purely a side effect, a result of the fact that you are not sampling the Fourier domain evenly. You're getting a sparse sample of it. Okay, so again, the problem that of imaging, of doing VLBI is to somehow recover what you think of should be the truth image, the top left, given information about the bottom right and the bottom center. And so there are a whole bunch of different algorithms that can do this. Some algorithms that are, decades old, the clean algorithm. Some algorithms that are relatively new, kind of associated with machine learning. And I'm happy to answer questions about these algorithms to an extent at the end of the talk, but I'm going to skip over the details of the algorithm and just kind of show what the output of these algorithms is. And since we only have incomplete data, since we only have a sparse sampling of the Fourier domain, that means that there are many different possible images that are completely consistent in some sense, completely consistent with the data that we took. So in the top left, I'm just showing a randomly drawn sample from the so-called top set of images that are consistent with the sparse sampling of data. So there are different assumptions, for example, different parts of parameter space, some hyperdimensional parameter space that you can explore, and you just construct these different images. And what you will notice if you look closely at these images is that they all kind of look like they have a ring, maybe, but some of them have more pronounced rings than others. Some of them look particularly blobby. Some of them have two bright spots or two predominant bright spots. Some have three, some have one. And I'll get into the consequences of this later, but I want to now compare the imaging reconstruction that happened for the Galactic Center to the imaging reconstruction, this kind of clustering question, the sampling question for the reconstruction effort for M87. So the EHT, the Event Horizon Telescope, also did this kind of procedure when it produced images of the black hole at the center of the M87 galaxy. And what you will notice here is that there's not nearly as much spread. And this, as it turns out, corresponds to the fact that M87 is about 1,000 times larger than Sgr. It has about 1,000 times more mass, which means it varies much more slowly. So 9 hours or 8 hours approximately for Sgr is like a year for M87. So, you take the observation, the amount of variation you expect to see in Sgr in the Galactic Center over the course of an observation is significantly greater than the variation you expect to see for M87. So M87 overall is just an easier source to image because of this time scale question. Okay, so you've run this imaging algorithm, you've run these imaging algorithms, plural, and you produce all these different images. Now what do you do? Well, what you can do is you can try and group all of these images into what are called clusters. And so, this is a very well-defined mathematical question. There are different ways you can pose the question mathematically, but at the end of the day, you're trying to identify groups of images that are similar in some sense. So, how much extended emission do they have? What is the radial profile of emission, so on. You can think of a whole bunch of different characteristics for this question. And you run this clustering algorithm. I'm going to run it on the left now on the Sagittarius A-star potential images. And so what I'm showing you here down at the bottom is just a whole bunch of different selections. So if we iterate through all of the different images that I'm showing on the top, the small images, and you group them, then you get these four different clusters. And at the end of identifying the cluster, what you can then do is take all of the images that belong to this cluster and average them together, just to get a kind of representative image of the cluster. Now, to be clear, this average of the cluster does not have to correspond to an actual average image that was reconstructed, but it is kind of representative. Hopefully, it picks out morphologically features that are representative of the cluster overall. And just for completeness, I'm going to show the same process happening for M87. You will be unsurprised to see that the clusters for M87 all look very, very similar. And then at the end of the day, you take these average images that you get from this clustering procedure and you average the average images together. And you get something like a representative image of the overall structure that you would expect to see, the structure of an image that's consistent with the data. And in the case of M87, there are some really robust features. So all of these clusters, all of these average images have a bright kind of a bright side on the bottom and a very clear ring structure. And so that's what you see for the M87 reconstruction, but that's not the case for the Sgr reconstruction. Again, some of the average images have what appear to be a very clear ring and three blobs with a blob that's hot, or a bright blob on the top, or maybe a bright blob on the bottom, or maybe no ring at all, or depending on what you count as a ring, no very clear ring at all, but just two blobs, and so on. So this is what I meant when I said I want to kind of warn you about what you should interpret from the images. These reconstructed images may be rather misleading. And just to provide a kind of concrete example of what I mean by misleading, I thought I would show a high resolution simulation where we absolutely know the ground truth. So I take a high resolution simulation of an accretion flow, and I look at it over time. I produce a time series, a movie of this simulation, and then I run it through the imaging pipeline. And so you can then ask the question, well, does the pipeline reconstruction correspond to particular features in the original simulation? We can actually compare the reconstruction to the truth and ask how similar or how different those two are. The upshot here is that the average image does not necessarily have to reproduce any individual frame. And moreover, it can have features that are incredibly misleading. So if you look at these 4 snapshots from the top, this is again coming from a high resolution GRMHD simulation. And I'll explain what I mean by that later. Sorry to keep pushing things off to the future, but effectively this is a high resolution simulation of what we think reasonably an accretion flow might look like. And so I've selected 4 snapshots from this overall movie. And so you see there's this kind of chiral structure, there's this thin ring feature, and there are some bright spots maybe corresponding to where you have what looks like filaments that are falling into the central black depression. And that's kind of characteristic of these 4 snapshots, but also of any of these snapshots that you pull from the overall time series. And so again, since we have the truth, since we have the snapshot, since we have the high resolution simulation, we can just actually average the simulation. And that's what you're seeing in the bottom left. So if we actually average all of the frames that go into the simulation, all the frames that we're simulating or we're going to simulate an observation of, you see something that is perhaps not so surprising given our knowledge of the snapshots. You see this dark region in the middle, you see this kind of thin, bright ring that looks particularly bright in the bottom right, maybe on the right-hand side more than in the bottom, and then you see this extended feature. Now, that's the high resolution average. You can then say, okay, well, I certainly cannot hope to recover a high resolution image. So what if I blur to the image, the best possible image I could get by constructing an instrument on the Earth? Again, remember that the size of the Earth limits the resolution that you can see. The larger your telescope, the smaller the features you can see. And so you blur the high resolution weighted average to the EHT resolution approximately. And the EHT resolution here is just represented by that circle, that white circle in the bottom right. And again, you've seen something that I think is not particularly surprising. Again, you see this bright ring of emission. It's particularly bright on the right and in the bottom. And you see this dark feature in the middle. Okay, so this is what we expect to see. There's nothing surprising. You then run this through the reconstruction procedure. So you simulate an observation with a whole bunch of telescopes distributed exactly like the Event Horizon telescopes are distributed. You run the imaging algorithms, you run the clustering and so on. And then you can produce an image that looks like the reconstructed image here in the bottom in the third panel. And I just, again, want to stress that this reconstructed image doesn't really look like any snapshot, right? You see these 2 blobs. So the 2 blobs don't correspond to 2 blobs in the EHT resolution observation. They don't correspond to 2 clear blobs in any of the snapshots. And in fact, one of the bright spots is on the top right, which you just don't see in any of the snapshots. And you certainly don't see it in the average images without this imaging reconstruction procedure. So when you look at the image that the EHT published, or the set of representative images, and you see these 3 different features, and you see that one of the features in the top right is particularly bright, you should look at that with some skepticism and not draw any inaccurate, inappropriate conclusions from it, because they might not be real. Now, to be clear, it is totally possible that there are 3 bright spots in a particular snapshot. Those 3 bright spots can absolutely be real. There are reasons to believe you should see bright spots. In fact, in the simulations, right, you do see that we produce a bright spot. Bright spots totally could be real, but you should not yet infer that these features are real. And in fact, you should not ever infer that the features in the images that we have published so far are real in this sense. So the problem then becomes, how do you identify which features are robust, right? Because at the end of the day, we have these great data. You can either analyze them in the Fourier domain, or you can try and gain intuition from the image plane. But if you want to use these data and learn something about the source, learn something about the black hole or the plasma that's around the black hole, do that kind of astrophysics, then you have to identify what the robust features are, because you could completely get the wrong idea if you don't do this. And I'll come back to what those robust features are. Now I'm going to kind of interlude and go to the second part of the talk, which is about how we actually produce astrophysical models of what's going on. But while I'm talking about this, I want you to have in the back of your mind, what are these robust features, or what could we possibly identify as a robust feature? Okay, so what's going on? So we think that the black hole at the center of the galaxy is in fact a black hole. I shouldn't have led that way. We think that whatever is at the center of the galaxy is a black hole, a very large supermassive black hole. We expect that there is a bunch of gas, and in fact we see the evidence of gas nearby. And so what we expect is going on is we expect there's a whole bunch of gas near a supermassive black hole. The gas is gravitationally bound, and it's falling onto the black hole. And it's not just gas, but it's plasma. This plasma has magnetic fields in it. And so the magnetic fields are being pulled with the gas as the gas falls or accretes onto the central black hole. And so if you just have this picture in mind, it turns out there are a lot of different parameters that could go into satisfying this model. And so I thought I'd just show these four neat 3D animations or 3D representations of what the gas could be doing. So in each of those, or in each of these images, there's a black hole that's very, very small on your screen. It's probably about the size of the dark region in the A that shows up in each of the panels at the top left, A equals 0.94, for example. It's about that size. And then we're showing contours of the density of the gas that's falling onto the hole. It gets more dense as it gets closer to the hole. And then these white lines are showing the structure of the magnetic field. So there are a whole bunch of different ways that you could drop gas and drop magnetic field onto the black hole. And ideally, if you want to build an astrophysical model, if you want to somehow compare the observations to the astrophysical models, you want to kind of sample the space of different possible scenarios for this accretion. But before we get to that, because that's a really hard problem, let's try and come up with the simplest model that we could think of, given that we know that there's gas and we know that there's maybe a black hole. Or at the very least, we know that there's some object with some mass. And if it has some mass, then it has some approximate size. And so the simplest model you can construct, or one of the simplest models you can construct, is a so-called one-zone model, which just means that we're going to assume that there's this uniform ball of matter that has some size, but it's completely uniform throughout. So it has the same number density everywhere. It has the same temperature everywhere. It has the same magnetic field structure everywhere. And from this model, we'll see, if we can gain any intuition for what's going on in the source and use the results of this model to kind of motivate what part of parameter space we should look in for the more complicated models. And so what are the inputs to this one zone modeling procedure? Well, again, we know the approximate size of the object. How do we know the size? We know it from just, for example, tracking these gravity observations and other tracking objects near the galactic center. We can estimate what the paths of the objects are, and so from this you write down some potential. You use your physics 1 knowledge to back out what the mass should be. You get an approximate estimate. So given this mass, an approximate size, the approximate distance from the galactic center, wherever this object is, to the Earth. And so you write down a very simple model. You say, okay, I have some object that's approximately, let's say, 3 times 10 to the 12 centimeters in radius, and that has uniform magnetic field strength, uniform number density, uniform temperature, and then say, okay, so what does this object need to do in order to produce observations that we see? And in particular, what does this object need to do? What are the, the temperature? What is the temperature of the particles? What does that need to be in order to produce the observed flux at a particular frequency, right? So if you literally just look up at the source and you count the number of photons that are approximately 230 gigahertz, you get a number. You get that it's approximately, I'm not going to give you in number of photons, but I'll give you in energy. So you get that this is approximately 3 Jansky worth of energy at this 230 gigahertz frequency. And so then you can ask the question, well, okay, what could possibly produce that amount of energy? You work out all of the math. There are some nice nonlinear equations. And it turns out that what you expect to be happening is you expect for there to be a bunch of ions, let's say, but the electrons are what matters here. You have a whole bunch of electrons and ions, but electrons that have some distribution of velocity. So they're going all different ways, but they have some average velocity in some sense. And there are magnetic fields in this region. And what the electrons are doing is that they're kind of orbiting around the magnetic field. So again, you remember your early physics knowledge of how do charged particles move in the presence of a magnetic field. If you have a magnetic field, the charged particles will rotate around the magnetic field. And charged particles, as they're accelerated in circular orbits, will emit radiation. And if they're moving particularly fast, then they will emit what's called synchrotron radiation. So it's kind of like a relativistic cyclotron thing. And so there are certain properties of this radiation. So you work all this out, it turns out to be self-consistent. The average energy, which is kind of like a measure of the speed, so the average energy of the electron in this uniform ball will be 10 in units of MEC squared, so in units of the rest mass of the electron. The number density turns out to be about 1 million particles per cubic centimeter, and the corresponding magnetic field strength is about 30 GeV. Okay, great. So here's my simple model. But as we saw before, the simple model probably doesn't explain what's going on. The image has some source structure. It's not just a ball, and also it's changing over time. We know that the time dependence is interesting. So the simple model is not enough. So what do? Well, you take this one zone model, you take these outputs, these approximate numbers, and you run a fluid simulation. So you say, okay, it's not just a uniform ball that's falling onto the event horizon. In fact, it's a huge gas that has some angular momentum, let's say, some magnetic field strength, and it falls and does something. So what does it do? Well, it obeys conservation laws, certainly. So you can write down conservation of particle number. You can't, or you don't expect to be creating a whole bunch of electrons or whatever. So it obeys conservation for particle number, and it obeys conservation of stress energy. So, like momentum and energy and so on in some relativistic language. And then, of course, it has to obey Maxwell's equation. So you write that down, you get a set of conservation laws. It's very complicated, and you write these laws into a computer, and you run a computer simulation. And you run a whole bunch of computer simulations, in fact. And you get, at the end of the day, from every single computer simulation, you get a description, a time series of what the density looks like, what the internal energy or the temperature of the gas looks like, what the velocity of the gas looks like, what the magnetic field strength looks like, as a function of both time and space around the black hole. And then you take this fluid description, this time series, and you simulate the synchrotron process. And you ask, okay, so all these different particles can be doing something, they emit light. At the end of the day, where does that light go? What does that light look like to us? So this is the full simulation procedure. Again, this is a computational question. So to be a little bit more precise about the simulation procedure, I'll just talk about some of the inputs to it. So again, in this fluid simulation step, what are the inputs? Well, the two main inputs are the spin of the black hole. So black holes have mass, but we know approximately what the mass is. But they also can have angular momentum. So this is a parameter we need to vary. We don't know a priori what the angular momentum is. So you choose a whole bunch of different possible angular momenta, and you run different simulations for that. You also don't know what the relative strength of the magnetic field is. It's possible that the magnetic field is very, very strong and it's, halting, the magnetic pressure builds up so much that it halts accretion in some cases, or it could be very weak. You don't know. So when you're doing this forward modeling procedure, you choose a whole bunch of different magnetic field configurations, a whole bunch of different black hole angular momenta. And for every single one of those, you generate this fluid description. Again, the angular momentum, I think, is pretty clear what that is. You can just spin up the hole. But when you're considering this magnetic field configuration, I just want to put in your mind the kind of dichotomy that we care about. So of course, there's an infinite number of ways you could put a magnetic field in. You can't simulate an infinite number of configurations, but what you can do is try and find limiting cases. So the two limiting cases are effectively differentiated by whether or not the magnetic field strength is strong enough anywhere in the simulation domain, anywhere in your accretion flow, whether it's strong enough to materially stop the accretion. And so if it is strong enough, if the magnetic pressure is approximately the same as the inward ram pressure, then the accretion is said to be magnetically arrested. And so this forms a magnetically arrested disk or a mad disk. Mad flows are kind of choppy, as you can see on the left, and there are these large regions that are low density. And so this is one side of the possible accretion scenario. The other side is the so-called sane side, and it just means that the magnetic field strength or the magnetic pressure is not strong enough to kind of halt the accretion flow. Sane for standard and normal evolution. So sane flows are of course, they're still turbulent, but they're much more steady than these mad flows that have this kind of choppy behavior. And I realize I should have commented, I should have noted that these are, that what you're looking at here are the profiles of the log of the density in the midplane of the simulation. So you have an accretion disk that's falling in, and I'm just slicing straight through the accretion disk and plotting how much matter there is as a function of time. And just to provide some units, I'm showing this time as we're marching forward, time in the GM over C cubed. And so 1 in GM over C cubed for the galactic center is 20 seconds. Okay, so those are the inputs to the GRMHD simulation, to the fluid simulation. But then, as I said, you take the output of the fluid simulation and you run it through these radiative transfer codes where you simulate what all the electrons are doing, the acceleration and how they emit photons and so on. And there are more parameters that go into this. So one of them is just the inclination. If you have a 3D simulation of the fluid, that's great, but are you looking at it straight down, or are you looking at it from the side or at some oblique angle in the middle? So you have the inclination. Another parameter that goes into this ray tracing procedure, this image generation procedure, is the thermodynamics of the fluid. So at the end of the day, your conservation law treats all of the matter as a fluid, or at least in this prescription, it treats it all as a fluid with a single internal energy. But remember, what you care about is all of the electrons that are going around the magnetic field. So you have to translate this one number, this internal energy of the fluid, into a kind of distribution function of what all the electrons are doing. How many are going very fast, how many of them are going slow. So there's some question about the thermodynamics of the fluid that you also have to input. And again, a priori, we don't know what that is. So these are the different parameters that you can vary when you're generating these potential forward models. So again, starting from the left, you have the GRMHD simulation, angular momenta, the magnetic field strength, in other words, whether it's matter sane. Then you also vary over the inclination, so in the orientation, how you're looking at the black hole system, and different ways to translate the internal energy into a distribution function for your electrons. I forgot I had this slide. Wonderful. So here's a little graphic representation of the different ways that you can do that modeling of the thermodynamics. So I'll just kind of repeat myself here and I guess say, when you're translating the fluid internal energy to an electron distribution function, what you're precisely doing is you're writing down some prescription for how many electrons you have at a particular Lorentz factor. So that's in the bottom left here, dn d gamma, effectively how many electrons are going very, very quickly. And then your constraint is that you want to match the overall shape of the curve, or sorry, the overall integrated area under the curve to have the right number density overall from the simulation, and also to have an appropriate amount of internal energy. And then it's also worthwhile to point out, I think, that it's very possible for the actual regions that you light up when you do this this translation, this thermodynamic translation. It's very possible for the regions that are lit up around the hole to be very different. So I'm showing you a snapshot from one of these MAD models with strong magnetic field, and a snapshot from one of the same models, and showing you where the actual photons would be coming from, given some choice about your electron distribution function, your electron thermodynamics. And I'm just rotating around, so there's nothing interesting time-wise going on there. And these different simulations, these different paradigms can end up producing very different structures, which means that at the end of the day, you may be looking at very different parts of the system around the black hole. So this is worthwhile to keep in mind. Okay, so this is where the slide I thought was following that. So at the end of the day, what do you get? You get a whole bunch of images potentially. So you can look at the images at different frequencies. So 86 gigahertz. You can also look at 230 gigahertz, which is what the EHT is observing at. But you don't only get images, you also get spectra. So you can imagine asking the question, how many photons come at this frequency versus another frequency, higher and higher and higher frequencies. At some point, you have to start worrying not only about the synchrotron radiation, but also scattering. So photons, enter this region with a whole bunch of really hot electrons, and so they can inverse scatter and gain more energy and so on. So you produce these observables from every one of your simulations, varying all of your parameters. You get these images at different frequencies. You get these maps of the energy versus frequency space. And then you get a whole bunch of different images because the parameter space is quite large. So for reference, there were many different people and efforts involved in this simulation procedure. So there were 6 different fluid evolution codes. There were 2 different imaging codes and 3 other codes that were used for validation. And then there was 1 Monte Carlo code to produce the spectra. The overall library ran over 4 different possible accretion states. So I talked about MAD, insane accretion. It's possible that you can feed the gas in from large distances at weird angles. So well, maybe not weird in a cosmic sense, but at different angles. So you can change your boundary condition, and you can get tilted disks. You can get wind-fed disks where you just have blobs that fall in at certain times. We surveyed 9 different possible angular momenta for the black hole. And then we also varied the possible fluid adiabatic index for the fluid simulation. So those are the parameters for the fluid simulation, but we also have these different prescriptions for the electron distribution function. So we had 7 thermal, 6 non-thermal. We looked at 9 different observer inclinations. And at the end of the day, we ended up producing about 6 million possible images and 1.25 million possible spectra. And if you add up how many data point or how much actual binary data corresponds to just these electromagnetic observables, turns out to be about 50 terabytes worth of data. And this is not including the fluid simulations themselves. So this is a pretty large amount of simulation data that you then have to compare. Okay, so now I'll get into the constraints. So there were 11 different possible constraints, 5 of which came from directly EHT image data, 4 of which came from other data that were taken at the same time, but that were not directly produced from this telescope array. And then 2 other questions, two other constraints coming from the variability, the time dependence. And I'll treat each of these in turn. But since each of the possible constraints can be rather mathematically involved. I could spend like 5 slides on every constraint. I'm not going to do that. I'm just going to give you a broad overview, and then I'll of course be happy to answer questions later on, or you can read the papers if you want to. Okay, so first talking about the EHT constraints directly. Well, the simplest thing you can do is you can just ask, what is the image size approximately? And so it turns out that the extent of emission in an image corresponds to something like the second derivative of the Fourier transform. And so you can say, okay, well, given the data, again, I want to find these robust features. So what will be robust? Well, maybe I don't know about the Fourier data at every single point, but I do have a good sense of how smooth things are in a particular region, let's say. It turns out to be the case. So you can measure or get constraints on what the second derivative is, and you can get constraints on the approximate image size, the compactness. So this is the first so-called pre-imaging constraint, the second moment constraint. And it turns out to be not that discriminating in the sense that 98% of the 6 million images that you could produce are all consistent with the data. Okay, so this is one constraint. Another constraint that again comes from the Fourier domain is just to ask, okay, given a simulated image, if I were to observe it, take the Fourier transform, is the location of the kind of zeros consistent with the data? And so what I'm showing you here on the right is a set of two different possible simulated images and kind of like their Fourier transforms. And so what I want to draw your attention to in the bottom row are these two different gray regions. And so effectively the question that we asked here was, okay, given the simulated image, the Fourier transform of the simulated image, is the location of the first place where these colored lines, this Fourier transforms, is the location of the first place that these colored lines gets low, goes to zero. Does it lie within this first gray region? That's constraint one, and constraint two for this VA morphology thing is, are the data points in the second gray region sufficiently small, or do they have sufficiently low power? And so on the left-hand side, we're showing an image that passes, and you can contrast this with an image that doesn't pass on the right-hand side. And so, this is another constraint you can do. Again, this is a robust feature of the data because you don't need to know about all of the data points, across the entire x-axis. You're only looking at places where you actually do have a fair amount of information. And if you apply this constraint, it turns out that about 80% of possible images pass this constraint. So it's not particularly constraining, but it's better than 98%. And it's also interesting because it means you're actually constraining models with just the pure EHT data. These boxes just label how the image on the right fails. Another thing that you can do is you can do model fitting. So you can say, well, suppose that I know I don't have a perfect high resolution image, but I do know that there are some geometric features that are reasonable. And so what are these geometric features? Well, one is kind of the width, the approximate diameter of this dark region. So if there is a ring, let's fit for its diameter and then come up with some distribution over time and ask if this distribution is consistent with the distribution from a potential model simulation. So this is the ring diameter constraint. You can also say, okay, I know that I not only have a dark region, but I know I have some donut around the dark region and that donut has some width. Is that consistent? And not only is that consistent in general, but it is the distribution of those widths, is the distribution of the width of the donut as a function of kind of angular location along the donut. Maybe it's really wide on one side and really narrow on the other side. Is that distribution consistent between the data and a particular simulation with a particular set of parameters? You can also measure the asymmetry. If the image is brighter on one side than the other side, is that consistent? This turns out to be these set of constraints turn out to be quite constraining, especially this ring width distribution constraint. In fact, kind of the most constraining of the constraints from the pure EHT data. So now I'm going to move on to some of the non-EHT constraints very, very quickly. Is the spectrum consistent? Do you have too much energy in places? Again, you can apply this constraint. Well, okay, maybe I should back up into a little bit more. So you can apply this constraint and say, in particular, for example, if you let's say you go to a high frequency, so the X-ray constraint is the rightmost data point, right? Most of these 4 data points in each of the frames. If you don't produce enough X-ray emission, is that a problem? And you'll see that there are these arrows here, which kind of imply that it isn't a problem because there are a whole bunch of ways to play with the electron distribution function, it turns out, and produce more emission in those regions. So this is one constraint. Are you producing too much emission in the X-ray or in the near infrared, which is the other data point? You can also apply size constraints, so the second derivative, second moment constraint at frequencies other than 230. So I mentioned that 86 gigahertz was one of the constraints. And so we're applying a kind of like a second derivative, second moment constraint from the 86 gigahertz data. Anyway, these are the non-EHT constraints. And then at the end of the day, you can apply all these constraints to all the models. What you want to do is you want to identify which models or which parameters belong to models that are consistent with all of these constraints, with these 9 that I've talked about so far. And this is what you get. I'm not going to walk through every single region, arc region, I guess, I don't know, arc in this plot, but I will point out that there are some general trends. So the models that are MAD, in other words, that have these strong magnetic fields, that have a particular orientation for their accretion flow. So the angular momentum of the accretion flow is oriented in the same direction as the angular momentum of the central black hole. So MAD, prograde, spinning. Also, what is the imaging inclination? Well, we seem to be looking down at the black hole. And we can also learn something about the electron thermodynamics. The electron thermodynamics is probably cool. So these are the surviving models. There are also some summary statistics for what are disfavored. So single temperature fluids are disfavored. This is, again, just a question of the electron thermodynamics. Looking at the system edge on instead of down. So edge on through the disk is disfavored. Retrograde simulations are also disfavored. So in other words, we think that it's from these constraints in particular, and given the set of models that we looked at, we think it's somewhat unlikely for the accretion flow to be kind of rotating around the black hole in a direction that is opposite of the direction that the black hole itself is spinning. Okay, these are the summarized constraints so far, but I said that there were 11 constraints and I've only gone over 9 of them. The other constraints are associated with variability. And you'll recall that in the beginning, I talked about how variability is a big factor in the analysis. It has to be, because we're not actually taking snapshots, we're getting these kind of average things and so on. So it's really worthwhile to consider variability. Okay, so how can you do that? So I'm going to just talk about one of the potential variability constraints, and that's the so-called modulation index constraint. And so mathematically what this is just you take a light curve. It doesn't even need to be a resolved image, though we did have image variability constraints, but you just take a light curve, the overall flux that you're getting as a function of time, and you ask kind of what is the spread in the variation versus time? What is the standard deviation of that, the sigma? And you divide it by the average signal there. So sigma over mu over some window, for example, a 3-hour window is what we chose. Though you can vary this and you can ask questions and confirm that it's a rigorous statement. But you ask this question: what is the sigma, the average sigma over a 3-hour window, divided by the average, the average variation in the signal over a 3-hour window, divided by the average signal in a 3-hour window. That's a number. You plot the distribution because you have historical information about Sag star, how much this is varying over time, historical information. You plot all of that. You ask if the distribution from the true data, from the observed data, is consistent with the distribution from any of the simulations. This is, I think, one of the most interesting results from the astrophysics side to come out of the analysis, because it turns out that almost all of the models that we have, almost all the fluid models, the simulated models, are too variable. This is, I think, rather surprising. I think that if you'd asked me, or if you'd asked us, 5 years ago what we would expect, we would actually expect that they're not variable enough. We expect, you add in more physics, you have a more precise treatment of the electron thermodynamics, you get more variability. But in fact, we saw that there's less variability. When you apply this constraint to the data with the other 9 constraints, nothing that we did worked. No model passed all 11 constraints. Which again, I think is kind of exciting, because it means that we have a ways to go. I guess I should very briefly comment that perhaps unsurprisingly, the sane models are less variable than the MAD models. This just ties back to that slide before where I showed the very chaotic MAD inflow with all these bubbles. So MADs are more variable than sanes, but still there isn't overall any model that passes all the constraints. Okay, so what did we learn? We produced petabytes of fluid simulations, terabytes of simulated observables, and part of this process, as part of this process, we learned that our fluid codes, again, I said there were 6 different fluid codes, there were multiple imaging codes, are all surprisingly, well, I shouldn't say surprisingly, are all very happily, we are happy that they are all consistent. They produce consistent predictions. So this was great. We compared our model against 11 different possible constraints. The EHT image constraint, right? So this VA morphology, this kind of geometric fitting, turns out to reject a whole bunch of models. So the EHT image does tell us something about the astrophysics. We learned that the prograde MADs are kind of favored. We learned that, single temperature. So we learned something about the fluid thermodynamics in the context of our models. But we also learned that most of our models are too variable, which again, kind of points us towards something to do in the future. And before I get to my kind of summary and future thoughts slide, I want to caution that our best bet models, so my bullet point number 5 here, and also the conclusions of bullet point 6, are all with respect to our prior. So, we did not simulate every possible spin. We only simulated 9 possible spins, only 9 different angular momentum states. So, we had some prior. We only sampled the space of possible distributions very, very sparsely. We believe the trends. So we believe that, prograde things are more likely than retrograde things. But, the fact that, for example, a plus 15/16 spin model, might do significantly better in one analysis than a plus 1/2 spin model, you shouldn't necessarily trust these things to a quantitative, precise extent because we only sampled our prior very, very sparsely. And, we didn't include all the possible physics. We didn't include, for example, viscosity. Viscosity could change things. So best bet models are with respect to our prior. Don't believe that a reported model that does very, very well is definitely what's going on, or that it's unlikely to change when we include more physics. Okay, so here's my one slide what's next kind of discussion. So evidently we need to improve our fluid model. We need to add something that will allow us to produce simulations with less variability to be consistent. How do you do this? Well, you add conduction, you add viscosity, you change the fluid composition, for example. If you include radiation in the fluid model, so I just talked about conservation laws for number density, for stress energy, and Maxwell's equations, but you can also add a photon fluid that transfers momentum and so on. So maybe radiation matters. We can also include even more constraints, so we didn't have any models that passed the constraints we have, but we can add more constraints and see what we learn from those. We have data from different years. We probably want to consider alternatives to the to our boundary conditions. So again, we just need to sample the parameter space a bit better. As I said, change the gas composition. In the future of the observations, what can we expect? Well, we expect at some point in the future, we will actually have high resolution black hole movies. And, we'll be able to get way more information from those movies than we get from, 16 blurry pixels. Hopefully at some point, we'll be able to actually track fluid parcels in the magnetic field near the horizon. That might tell us something about GR and connections between black holes and relativistic jets. We might be able to put satellites in space and overcome the limits of the size of our planet, which would be great. Get really, really high resolution movies, and also look at time-dependent signatures in different parts of the images. There are reasons to believe that black hole movies should exhibit certain echo periods in different regions. So we would also be able to look at that. So that's the future. Before I say thank you, I want to just point out that the EHT collaboration comprises hundreds of people, and none of this would be possible without everyone working very hard. And I'm very much honored to be a part of this really large collaboration that's doing some really impressive work. The last time we all met in person was 2019 before COVID, but we're going to be meeting in person in Granada, Spain very soon. So that's also exciting. We'll be able to update the photo. Okay, so with that, thank you everyone for your time and your attention, and I'm happy to take any questions.
Thank you, George. Indeed, it's a massive and very interesting work. Let me start with some questions. I see one question in the YouTube channel. How much does the distance uncertainty between the different EHT observation points affect the observations? Are cartographic corrections relevant? Are atmospheric effects relevant? I'm going to copy this question in the chat in case you.
Yeah, so I think what you're talking about for distance uncertainty, I think what you mean is in this VLBI question, when you have this plot of all the different baselines, so the distance on one of these plots, there is some uncertainty because we don't know down to the nanometer how far away two different telescopes are. So I am going to give a very hedged statement here because I don't work on this particular thing, but I know that people in fact use VLBI to measure distances on Earth. So it's not like someone got out a map in the Mercator projection or choose your favorite projection and made some estimates. There are some very, very sophisticated things that go into ensuring that these distances are sufficient to do this kind of a measurement. Again, also remember this is 1.3 millimeters, so you don't need to go down to the nanometer scale at all. You just need some kind of accuracy. You need some estimates on the scale associated with your wavelength. There's also a fringe fitting step. So there's a whole bunch of technique that goes into tamping down all of those uncertainties. Does the atmosphere matter? Yes, the atmosphere absolutely matters. So if you look at an actual track, which is a set of observations, you'll see that we point the telescopes at the Galactic Center, for example, or at M87 for like 10 minutes or whatever, and then you point them somewhere else where you know exactly what you expect to see, and this is your calibrating source and so on. So you have to take into account all of these different effects, the weather model. So I cannot open the chat actually because I don't know where my cursor is. So if I miss something in the chat, tell me and I'll come back to it. I'm sorry.
Okay. Thank you. If the coordinators have a question, they can unmute themselves. I'm going to read another question. Okay, there's another question about like what sets the number of clusters? Why do you show 4, or what there are just 4?
Yeah, that's a great question that I should totally be able to answer. And I cannot answer why 4 was chosen. I do know that if you kind of change your clustering algorithm, you get very similar results than this kind of analysis was done, but I don't want to say something wrong. I don't know exactly why it was 4.
Okay, Jorge.
Hi, thanks for a very interesting talk. So at the beginning, you showed like the difference distribution you get from our galactic center and from M87. Mm-hmm. And you said, well, one of the differences was the scale, the time scale for both black holes. Yes. But I was wondering if the fact that our galactic center accretes very little also makes a difference. Or in other words, can you get the accretion rate somehow from the images or from the data?
Yeah, so right, so to add numbers to that statement, you can estimate the M87 accretion rate to be something like 10 to the minus 6, 10 to the minus from their modeling uncertainties in this characteristic Eddington mass rate. And you compare that to the Galactic Center, which is something like 10 to the minus 9. Again, with modeling uncertainty. So, that's 4 orders of magnitude difference, maybe. So one way that you can constrain this is with these one zone models. So you do have an estimate of the approximate size of the source. You have estimates that the gas should be approximately virial or maybe slightly subvirial, for example. And so from this, you can estimate directly kind of what the number density should be. I will also say that, if you run a simulation and you bump up the accretion rate, it just looks different. So maybe this is a more direct answer to your question. If these radiatively inefficient accretion flow models are correct, which we do believe, or we at least believe that they're representative, there are limits on kind of how much on how much energy you can actually, or sorry, on how much stuff you can put there. Because if you put too much stuff there, it produces too much emission. Or if you put too much stuff there, the disk gets too large. And it turns out to be the case, and I think this is absolutely incredible, that for M87 and for the Galactic Center, even though there are these very different accretion rates, they do end up corresponding to very similar looking images. And this didn't need to be the case. But I hope I've at least somewhat responded to the question.
Sure, thanks.
Okay, yeah. Of course.
Okay. Thank you. There's another question in the YouTube channel. What kind of new algorithms would need to be developed to try to overcome the variability of the reconstructed images in order to produce black hole movies?
So I think there are two parts to that question. One is what kind of algorithms would need to be developed to overcome the variability. And the second one, which might seem like it's the same question, but I think isn't, is what kind of algorithms do you need to produce the black hole movies? And I am going to start with the second question, which is that I really think, in order to gain confidence, for us to gain enough confidence to, publish a movie and say, we think that this movie is, has some robust features in it. I really think you just need more data, because over time, if I can remember where these pictures are, right? In order to produce a movie, right? Ideally, you want to have some idea of a full snapshot every minute or so. Let's be generous and say every 10 minutes. So that means that you take all these different colors and you choose one point from each of the colors. And you try and produce a frame from that. And I think that that's just very challenging. So I actually think that the main technical issue with producing movies is that you want kind of more baseline coverage. So how do you get that? You get that by adding more telescopes all over the world so that you just get more data points. So I think for movies where you want confidence in the features or in the movies in some sense, I do think that the solution there is not really algorithms, it's instead adding more telescopes. But the first question is, how do you improve the algorithms to kind of learn more given what you have? So maybe you can't produce movies, but maybe you can learn more. I think that's a pretty challenging question, because at the end of the day, you want to be sure that your algorithms are not missing something. So for example, we could have developed algorithms, they would have been horrible algorithms, but we could have said, come up with an algorithm that produces the best fit circle for the data, and then you would have a lot of confidence in that circle. But if you didn't realize that the circle model is wrong, that, it should be a donut, then you're missing something, and you can improve the algorithm more and more and more. But if you don't know what you're looking for, at the end of the day, you have to make some model assumptions. And I think that, the way that you do this is actually through theory. Of course, I'm biased. I produce simulations a lot. So maybe I'm too biased to be answering this question, but I think that my answer is you need to really understand what all of the different possible model spaces in a very fundamental way. And then you can use that to kind of feed back in on the algorithms. I'll also just end that by saying, there have been recent developments in algorithms that say, okay, we expect to see this kind of structure. So this allows us to get what's called super resolution. So maybe the Earth only tells you can see something at 25 microarc seconds, but we expect that there's some overall structure in the Fourier domain that has, again, been trained by the theoretical movies, by the theoretical assumptions, that allows you to get down to like 15 microarc seconds and so on. So there is movement in the algorithm front, but I think that you really want to motivate it with more theory. No, sorry. Now I'll actually say last thing. Also, it's still a theory question, I think, but how do you build in knowledge of overall average structure into your algorithms, right? So maybe you only have a single data point at it for a single time, but you have some expectation from theory about how much the source can change over 20 minutes. Maybe it won't change significantly over 20 minutes, in which case you ask the question, okay, how do you build that information into the algorithm? Kind of some time dependence, some smoothness of your time dependence, also multi-frequency stuff, and so on. Okay, now I'm done with that.
Thank you. I have a follow-up question, which will connect to the other question that is on the YouTube channel, which is like you said, like this GR-MHD simulations are perhaps too variable. Then and then connected to what you were saying, and with Sagittarius A star, it seems like somehow we're seeing an average. So how is this like time variability enter into account there? Is there a way to easily understand why you think it's too variable? Of course, you know, because the black hole is smaller. But in some question, how can this average data can tell us that our simulations are too variable in some sense? Is there an easy way to understand that?
I think the best way for me to respond here is that you will notice that the second to last constraint, the LC variability constraint, I have not put in the derived from EHT data section. So in fact, for this particular variability constraint that I was talking about, where the simulations are too variable, this is not something that comes out of the average image. This just comes out of ALMA light curve data. Well, not just ALMA light curve data, but light curve data, where you just look at the source. You don't try and make a movie at all. You just count all the photons. You don't care about exactly where they came from. You don't care about the image features. And you ask, how many photons am I receiving as a function of time? So that's where this light curve variability constraint comes in. It's not from the image. That's a very good point. One constraint that I didn't mention is this 4 gigalambda variability. And so that does come from EHT data. You ask about, you know, what's the variability at a particular place in the Fourier domain. You know, you can also ask questions about the structure. You know, how much do you expect small scale features to change versus large scale features to change? And there, the constraints actually aren't as problematic as the overall light curve variability constraint. So you can get variability information from the EHT data, but my statements about the variability in models overall being too much was a pure, you know, integrated light curve statement. It wasn't purely from the EHT data. Yeah, and I guess I'll follow that up by saying, you know, you could ask the question, well, you know, why didn't we know this before? You know, because I'm saying it doesn't have to do with EHT data. And so the precise statement about variability is, for the models that match the EHT data constraints, that match those 5 constraints up above, those models are in general too variable. And of course, I could write down some other crazy model that doesn't look like a donut at all that reproduces the variability. So, you know, it's kind of like this game where you want to match the EHT constraints, but you can't just match the EHT constraints. You need to match, you know, what's going on in the larger ecosystem of observations.
Okay. I think we have more time for another question that it's here in the YouTube channel. Says, combining Newton's constant and the speed of light is not enough to construct a time scale. A mass scale is also needed. What mass was used? The black hole mass. What does this characteristic time represent?
Yep. So yeah, that's exactly right. Of course. So the time scale is in this box, the second row on the left, GM over C cubed. And so I guess the answer to this question depends on how much you know GR, but effectively there's a characteristic size of an object in GR, the event horizon. And the event horizon, the size of the event horizon scales with the mass of the black hole, as it turns out. It also cares about the angular momentum, but a good general kind of intuitive picture to have is that the black hole event horizon has a radius of something like 2 times this GM over C squared number. And so the time, this characteristic time that I've written down here, if you multiply it by 4, it's kind of like the amount of time it would take for light to pass through, this is a very non-GR statement, to pass through one side of the event horizon and come out the other side of the event horizon. Obviously, that's not going to happen because that's not what an event horizon is. But it's about the time it would take, you know, you multiply this by 4 or multiply it by 30 is a better number for GR. It's about the time it would take for light to kind of go around the black hole. So again, given a black hole mass, you can figure out what the event horizon size would be, and then you can ask the question, how much time does it take for light to go around the black hole? Precisely, this 20.4 seconds is just the light crossing time for one black hole mass. But if you want a more physical, intuitive picture, you multiply this number by anywhere between 5 and 60 or whatever, which, 5 and 60 in astronomy, they're the same number. So you multiply this 20 by 5 or by 60, and that's the amount of time it would take for light to kind of travel around the black hole at a reasonable distance.
Okay, thank you, George. Oh, I see. Roberto, sorry, I missed you. Go ahead.
Right. Very nice webinar, George. So I was wondering, because since the Earth, we are within the galactic plane, so we are kind of observing the black hole in a very particular position.
Yes.
Is any other black hole candidate to be observed, like to learn more about I don't know, Andromeda black hole? Is it possible to reach with the?
Right. So I don't have this plot. I should have included it as a backup slide. So there's all right. So the direct answer to your question is, there may be another one. Well, so actually, the zeroth order direct answer to your question is, we also looked at M87. So we looked at the Galactic Center black hole, and we looked at the M87 black hole. So that's sample size 2. We expect, just from general arguments, that maybe there would be another black hole that we could see. We don't know about it yet. It's probably unlikely that we don't know about it. But anyway, just from general geometric arguments. But there are two numbers, or there are two criteria for being able to see this, or being able to see a black hole. One is the size, and the other is the flux. So it does need to be bright enough. And as of yet, the other objects that we know of are either too small or too dim to be seen. Again, by general geometric arguments, maybe we would expect that there's another one that we somehow don't know about, but I don't know. So I think that really our best hope for getting these high resolution images is probably or movies probably lies with the Galactic Center or with M87, which we've already imaged. However, if you go to space and you don't care about this high resolution movie, and you just kind of care about general features of the source, if you go to space, we can see, maybe hundreds more black holes. You won't make movies of them, high resolution movies, or at least not in my lifetime. Well, I guess I should knock on wood, yes, in my lifetime. But I don't think that, we'll have high resolution movies in my lifetime of hundreds of black holes, but you could make some measurements, learn something maybe about their masses or something, but. Yeah.
Okay, thank you.
Yeah.
Okay, thank you very much, and thank you everyone for attending this last season of this webinar of this season. We will resume maybe in August, September, and I'm trying right now to convince Jorge Cuadra to be our first speaker. So now I make it public, so there's more pressure on that. And thank you everyone, and thank you, George, very much for this interesting webinar. And then I can imagine people can go to your webpage if they have follow-up questions, stuff like that. So thank you very much, and have a nice break. Bye-bye.
Thank you.
Okay, we are not live.